This is acetic anhydride. In almost every country, it's a heavily controlled precursor, making it nearly impossible for a home chemist to buy without a license. But today, I'll show you a forgotten and rare method to synthesize it in bulk using two common reagents, vinyl acetate and acetic acid. No mercury, no complex setups, just pure chemistry that actually works. I discovered this procedure thanks to a fellow chemist named Waffles, who shared an archive of rare patents with me. This is the vinyl acetate method. The chemistry is elegant. In the presence of an acid catalyst, these two react to form ethylene diacetate, which then decomposes into acetic anhydride and acetaldehyde. While you could make vinyl acetate from acetylene and toxic mercury salts, I'm using the store-bought reagent to keep this safe and efficient. We start with equimolar amounts and a few drops of concentrated sulfuric acid and start gently boil the mix. Once boiling temperature hits 75 degrees, the reaction begins. As the temperature climbs to 90, our byproduct, acetaldehyde, begins to distill. Since my lab is currently at a freezing -5 degrees Celsius, I can catch it as a liquid. Look at those crystals, that's paraldehyde forming in real time. By the end of day 2, I've distilled 105 grams of acetaldehyde, about 10% over the theoretical yield, which means some vinyl acetate and acetic acid carried over with it. Now, a quick pro tip for those of you who don't live in a freezer. I'm lucky that my lab is at -5, so I can easily condense and weigh the acetaldehyde to track the reaction. But what if your lab is at 20 degrees? At that temperature, acetaldehyde is a gas. In that case, you can use a gas bubbler like this. Fill it with a bit of inert liquid and it will bubble as long as the reaction is generating byproduct. While you won't know the exact yield, it's a great visual indicator to tell you when to stop. Alternatively, you can weigh the entire boiling flask before and after the run. The mass loss will tell you exactly how much acetaldehyde has escaped. But now, the reaction must be stopped. To neutralize the sulfuric acid catalyst, I'm adding 5 grams of anhydrous sodium acetate. This is crucial. If we don't kill the acid now, it will continue to char our product during the next step. Now I've set up a simple distillation to separate the crude mixture from the salts and the accumulated polymers. As the distillation progresses, look at the boiling flask. It's a mess. A thick black resin has formed, a consequence of the long boiling time and that extra bit of sulfuric acid I added earlier. But don't worry, it won't stop the anhydride from coming over. Here is our crude distillate. It's a mixture of acetic anhydride, acetic acid, and some leftover ethylene diacetate. It needs proper fractionation, but first, we have to deal with that flask. Don't believe everything you see on Nile Red. Organic chemistry isn't always about beautiful crystals. Usually it's a battle against the tar. If you've ever had a reaction go south and leave you with a carbonized nightmare, you know the feeling. If you watch channels like Nile Red, you might think chemistry is always clean crystals. In reality, it's often a battle against resin. But don't rush to the heavy chemicals just yet. Since this mess contains water-soluble salts like sodium sulfate and acetate, I started by washing it with plain hot water. As you can see, this actually removed the bulk of the gunk. However, the glass is still heavily stained. Time for the nuclear option, Piranha solution. I pour in some concentrated sulfuric acid, add a few milliliters of hydrogen peroxide, and apply gentle heat until it starts eating the organic residue. If the reaction slows down, I carefully add more peroxide. Safety is paramount here. Never use hydrogen peroxide concentration above 35% for this. Ensure there are 0 organic solvents left in the flask before adding Piranha, or you'll risk an explosion. If you do it right, the result is magical. The dark stains vanish and the flask becomes crystal clear again. This is the part of chemistry they don't show you in textbooks, the constant battle for clean glassware. To get high purity anhydride, simple distillation isn't enough. The boiling points of acetic acid and the product are too close. I'm using a vacuum-jacketed column packed with Raschig rings. It's 5 times more efficient than a standard Vigreux. We're aiming for a steady 1 drop per second. Once we pass the 135 degrees mark, we're collecting the good stuff. Now for the satisfying part. Notice how the anhydride droplets trap air bubbles and sink? It's denser than water, but that bubble trapping behavior is something unique I've only seen with this substance. To prove we actually have acetic anhydride, let's add a few drops of aniline. After a short while, a white precipitate forms. This is acetanilide. Success. From this run, I pulled over 150 milliliters. My yield was about 60%, lower than the patent's 90%, likely because I was a bit heavy-handed with the sulfuric acid. But for a method this accessible, it's a game changer. Thanks for watching and stay curious.